Hello everyone, my name is Jees Augustine. I am from the Database Exploration Lab at the University of Texas at Arlington, along with Suraj and Professor Gautam Das. This work is done in close collaboration with Muhammad and Professor Sanjudi Basu Roy from the Big Data Analytics Lab at the New Jersey Institute of Technology. Our work is titled as a generalized approach for reducing expensive distance calls for a broad class of proximity problems. Without further ado, let us get deep into the problem. Here we try to give a very brief and a broad definition of proximity problems for the benefit of the audience. Proximity problems is a class of problems in computational geometry which involve estimation of distances between objects. Classic examples of proximity algorithms include minimum spanning tree, clustering algorithms, k-nearest neighbors, and many more. One of the key aspects of all of these algorithms is the notion of distances. So here we try to establish this notion of distances through some real-life objects and their relationship between them. Let us take the example of cats, dogs, and balloon toys to establish the notion of distance here. It is good to note that the objects which are similar tends to have a very minimal distance between them, thus tends towards a 0, and if the objects are very dissimilar, they tend towards a larger value. For our consideration, we put it as 1. In this example, you can see that both cats are very similar, and they are represented by a short distance represented by the small length of the arrow, which is the same between the dogs and the toy animals, but the distance between a cat and the toy animal is very large because of the large dissimilarity between these two objects. This is true for most of the objects in real life. Thus, if you replace the cats and dogs with a set of documents, you can actually group documents which are similar from those documents which are not similar. Now that we have established the notion of distances, let's quickly get back to the proximity problems. There are numerous internet giants like Google, Microsoft, Swiss Cows, DuckDuckGo, StartPage, who try to solve these proximity problems on a day-to-day basis. For example, trying to find out a document which is as closer as to the keyword which is presented. These applications are not limited by the document search. They span across a wide range of applications such as maps. There are numerous applications including finding the minimum spanning tree, finding the tour of a given set of points of interest on a map which are separated by roads. They use APIs like Google Maps API, Bing API, and the Waze API in order to compute the distances between various POIs. Another example for multimedia proximity search is the reverse image search, where the task is to find out a set of objects which are as closer to the presented query object. Along these lines, there are numerous medical applications such as MRI scan comparison, fMRI scan comparisons, CAT scan comparisons for disease diagnostics. After having been presented with the ubiquitous nature of proximity problems in real life, we would now like to establish that the distance computations are actually expensive. Take for example Google Maps. As you can see, for the static maps, for every 1,000 requests, you will have a total of $2. Imagine you are a third-party application developer, then you will have to incur all these costs in order to develop a tour. These expensive distance computations help us to establish the notion of oracles. Oracles are entities which, when presented with a pair of objects, provides you with the exact distance measurement between these two objects. However, these distance oracles are expensive, thus computation of all pairs of distances is impractical, and with scale it becomes a challenge. Thus, our overall aim in this work is to reduce the total number of the expensive distance calls at the expense of local computation. For this purpose, we took a very close look at the proximity problem solutions to evaluate for the origin of the expensive distance calls. And we can find that all of these distance costs are associated with the if statements. Like, let's say if the distance between OI and OJ, being two different objects, is greater than or equal to distance OK and OL, another two pair of distances, do something else. So the majority of the distance computation comes from the if statements. So this is very true in the case of k nearest neighbor graphs. So we basically decide if that is nearest to k nearest to a given object based on these distance computations with the other objects. Similarly is the case for minimum spanning tree. You decide whether an edge to be added into the tree based on the distance comparison between pairs of objects and all the candidate edges that can be added to the tree. Similar is the case for clustering. You wanted to find out the cluster centers and points around it such that the inter-cluster distance is tight and intra-cluster distance is maximized. So in all of these conditions, the if statements which evaluate the distances between pairs of objects actually consumes the expensive distance calls. So somehow, if we can avoid these distance computations, or we can overlook these distance computations, it will help us in reducing the total number of distance calls. Before we dive deep into the solution portfolio, we would like to establish the nature of the distances in our work. We have focused our attention onto distances which are in the metric space. Simply, if two objects are exactly the same, their distances is 0. And if two objects are similar and are very close, and if one of these objects are very far away from a third object, then the distance from the first object to the third object is also large. As you can see in the second part of this image, there are two hats and a rabbit. The distance between two hats are small, and distances between one hat and the rabbit is large. Consequently, the distance between the rabbit and the other hat is also going to be large. Now we will introduce a novel formulation of the problem, a system of linear equations, as direct feasibility test. In this, we represent each of the distances as variable. For example, if you have a known distance xy is equal to 0.6, you introduce a variable xxy minus 0.6 less than or equal to 0, and xxy minus 0.6 greater than or equal to 0. If the distance is known, you simply initialize it as xab minus 1 less than or equal to 0 and xab greater than or equal to 0. After which, we introduce the triangle inequalities for each of the triangles in the system, such as xyc for a triangle, xy minus xxz minus xxz will all less than or equal to 0. Thus, we form the system of linear inequalities and we solve the system of linear inequalities to check for the feasibility region, which corresponds to the if statements, and you can simply skip statements if this condition does not meet. This is a novel formulation. As I said before, they form a linear system of equations. The number of equations is in the order of n square. The number of equations corresponds to triangle inequalities in the order of n cube. Of the shelf linear inequality solvers are expensive, limiting its application to only small graphs. Since the direct feasibility test is only limited to small graphs, we have searched for a more practical approach towards this problem. in a graph theoretic approach. So let us assume the suit of cards and the clubs, spades, and the hearts and the diamond. And let's assume that you know the distances between some of these objects and you do not know the distances between some of these objects. Now let us take a close look at the if statements which causes these expensive distance oracle calls. And we ask ourselves, can we rewrite these if statements as the lower bound of the distance between OI and OJ greater than or equal to the upper bound of distance between OI and OK? Then you can avoid the expensive distance calls, and if you do not succeed, you can still go ahead and do the distance computations. So we started looking at these opportunities where we can actually avoid the distance computations. But for this, we need to calculate the upper and the lower bounds more accurately for each of the unknown edges. Well, hey, here's the exactness genie, which says even if you replace the actual distance computation with the upper and the lower bound computation, the answers that you obtain from all these algorithms will be exactly the same as the answers produced by the algorithms without the upper and lower bound computations, by which I mean the exact same length of the minimum spanning tree, the exact same cluster and intra-cluster distances in clustering, exact same k nearest neighbors. Now the problem of reducing the number of distance calls has been transformed into efficiently and exactly calculating the upper and lower bounds for the unknown edge. The upper bound computation is far more simpler. All you have to do is to find out the shortest path from one endpoint of the unknown edge to the other edge point, and that shortest path's length is the upper bound. However, the lower bound computation is far more harder. To give a perspective, let's take an example here. Here you need to find out the lower bound for the edge, unknown edge xy. So let's say there is a known edge OI, OJ in the graph, which you see in the middle as represented by a green edge. You find the shortest path from X to one of the known endpoints, and from the end of that known endpoint, you'll have to find the shortest path to the other endpoint of the unknown edge. And then all you have to do is to wrap these two shortest paths around the edge, and that gives you the lower bound. And you will have to find out this lower bound edges using each of the known edges in the graph, and then you have to declare the maximum as the answer. We introduced the query and update model problems in response to a query edge, how to obtain the upper and lower bounds, and if any of the edges is resolved, how to update the data structure to get the latest upper bound and lower bound later. There is an existing dynamic programming approach by Wong and Sasha, which is in the cubic algorithm. But we introduce a new solution framework inspired by Dijkstra's shortest path algorithm titled SPLUB, shortest path lower upper bound algorithm. Imagine you do not know the distance between two convex cuts that you see, and you need to find the lower bound and upper bound of the distance between them. So what do? We try to find out the shortest path from this contact card to all the objects in the graph, from both ends points of this contact card, as you can see. Now the upper bound is simply the shortest path between these two contact cards. The lower bound, on the other hand, is very hard to compute. So inspired by Dijkstra's algorithm, what we do is we take a given and a known edge in the graph, which you can see in the bottom. You calculate the shortest path distance from the unknown edge point to one of these edge points of the known edge, and you do the same for the other edge point to the other edge point of the known edge element. And then you calculate the lower bound as follows. You take the known edge and subtract the values from the other two shortest paths, and you obtain the answer. You continue doing this for each of the known edges in the graph, and then you take the maximum of the lower bound and declare it to be the answer. The time complexity of this algorithm is exactly the same of the Dijkstra's algorithm, as it is evident from the algorithm itself. This scales very well to the medium to large size graphs. It finds the exact answers as that of the cubic algorithm, which was proposed by Sasha and Wong, but this does not scale to very, very large graph settings. Thus, in order to scale up to the very, very large settings, we do the approximate lower and upper bound computations. It is heartbreaking to know that they produce looser bounds. Upper bounds may be larger than the tightest upper bound, but lower bounds may be smaller than the tightest lower bound. But we unlock a new power to solve the graphs of very, very large settings. Exactness alert once again. For approximate LB and UB, the bounds are just approximate. We produce the exact same answers as that of the proximity algorithm. We do this at the expense of marginal increase in the number of oracle calls. To give you an insight on designing algorithms for large graph settings, we would like to take you back to the Dijkstra's based solution once again, and we would like to point out to a key step there. Here you can see that for calculating the lower bounds, we have used the shortest path between known edges and unknown edge endpoints. So we ask this question to ourselves: for scalability, can we remove all the shortest path computations from the equations just by replacing it with straight edges between these 2 points? So now it should form a triangle in order to find the distances between unknown pair of distances. Thus you produce an algorithm that scales a very large setting based on triangles and the lower bounds computed from that. So the actual details are presented in the paper. So basically you find out intersections of the pairs of nodes which has common endpoints, and you find out the lower bound distance based on that. For analyzing our results, we use 3 separate data sets, all real life data sets: SFPOI, Flickr 1 million dataset, and Urban For comparison, we use the state-of-the-art algorithms in order to be compared with our results. So ADM, LESA, and TLESA, details of which can be found in our manuscript. The glimpse of the results portfolio, you can see the lower bounds produced by the ADM and SPLUB are exactly the same, which is the same case for the upper bounds. The tri-scheme lower bound, which is the approximate lower bound, is much better than the TLESA lower bounds and the LESA lower bounds, as you can see from these pictures. Let us take a quick look at the answers for the PRIMS algorithm. So you can see that the ADM takes a very large amount of time, and SPLUB takes a fraction of the time that is required by the ADM, and tri-scheme is blazingly fast. You can don't even see in these graphs. Here is the glimpse of the distance save that we obtained using PRIMS algorithm. Here you can see multiple fields. We would like you to take a look at only the 2 fields which are given the last 4 columns: the LESA, the save, the TLESA, and the save. So you can see that as the scale increases, your distance save ups go up, and it is incredibly doing very well against LESA and TLESA in the order of 63 to 51%, and even the 63% is in the order of millions of distance calls. There are more details in the paper. These are from various proximity algorithms, the drawbacks of the proximity competitive algorithms, proof of concept as a result from direct feasibility test, scalability experiments, computational overheads, response to varying parameters in PRIMS algorithm. Please take a look at our work for more details. Thank you.